Hello everybody and welcome to this SCIA Engineer concrete rib design webinar. Today I'll talk about how to model, calculate and reinforce concrete ribs within the SCIA Engineer software. I'll start by giving a quick overview of what we're going to handle today. And I'll start by talking about the different approaches on how to calculate concrete ribs within SCIA Engineer. There are two main approaches, where the first approach we're going to use separate 1D elements and plates that work independently. And we're going to try to integrate the forces of these two elements by using integration strips or integration members. While with the second approach, we're going to use a ribbed floor or ribs that are bound to the plates themselves, where the rib and plate work together as one. I'm also going to talk briefly about how the internal forces are integrated for these separate elements into one rib cross-section. I'm also going to talk about how SCIA handles the reinforcement of these ribs for these two different approaches. And then finally, I'm going to talk briefly about the determination of the rib effective width and how SCIA handles that automatically within the software. And for this webinar, I created a very small, simple model where I've started off with a regular beam plate model where the beams and the plates have been modeled with the center line the same for both the beam and the plate. If we're talking about actual ribs, the beams are falling underneath the floor. So for the second model, I've given the beam some eccentricity, minus 300 millimeters, so that the top of the beam falls together with the bottom of the plate. And then for the third model, for the third plate, I've created actual concrete plate ribs. And you can see that for these plate ribs, they are bound to the plates themselves. And one of the things is that if I want to copy these ribs, then I'm not able to copy these ribs because they are bound to the plates. And you can see that I can only copy these separate beams. And if I want to copy the ribs themselves, I'll need to copy the plates as well, since they are working together as one composite element. I can create this ribbed floor by using a ribbed slab or the ribbed slab command. I can add in ribs into a certain plate if I want to, but there is a third option to start from this first model where I have the beams and the plates as separate elements. And I can select the members that I want to connect as ribs. For example, if I want to connect this middle element as a rib, I can select the plates and the beams that I want to connect as ribs. I can run the connect members nodes command. And if I run this command, there is this option to connect 1D members as ribs. If I use this option, I gotta watch out, because right now, if I would calculate the model, this connect members nodes command is set automatically. And if I do not deselect this option, all of the members will be connected as ribs automatically. So I really gotta watch out that I deselect this afterwards, because otherwise all of my members will be connected as ribs, which is not what I want. So I have this model where I have the beams modeled as ribs and where the beams modeled as with an eccentricity. And for this second model where I have the beams modeled as with an eccentricity, I also inputted an integration member where I set the width of my integration member to 1 meter to the left, 1 meter to the right, and 10 centimeters at the bottom and at the top. And you can see at that point an integration member is created. The reason why I took 1 meter is because if I take a look at the automatic or into the width of these ribs that are automatically calculated, the width for these elements is also equal to 1 meter to the left and 1 meter to the right of this rib. And then finally, I also created a 1D beam where the cross-section of that 1D beam is equal to the cross-section of one of those ribs, where you can see that this cross-section also has a width of 2 meters. I've also loaded all of these elements with the same load, so this 1D member is getting a load of 25 kilonewton meters per running meter, which is the same as the plate. And that is basically it. And now if I calculate the model, I can start looking straight into the differences between the second and the third plate, where I've modeled the beam with an eccentricity or where I've modeled the beam as ribs. And before I look at the results within SCIA Engineer, I have a quick overview between the differences of the concrete ribs and the regular beam and plates with the integration member. And the first difference, you've already seen a little bit, but with the regular beam and plate option, you have a little bit more flexibility when you're modeling the elements. The beams can be copied. You can easily set the eccentricity of the beam, while with the concrete rib, you only have top, bottom, and center. But also with integration member, you can change the width of the integration member easily. You can easily add in integration members or delete them without changing the results, since the integration member is purely post-processing information. While if you make changes to the concrete ribs and change the effective width, for example, you'll have to recalculate the whole model. On the other hand, the concrete ribs also have a few advantages, and you can see here for the internal forces, both options are able to integrate the design forces. But with the concrete rib, there are a few additional options that I'll talk about later today. And you can also see that for the concrete rib, the effective width can be automatically calculated, while for the integration member, I had to set that 2 meters myself, and I need to set that manually. And then finally, if you look at the reinforcement, we can give the integration member some type of cross-section to run a reinforcement design and check. But with the concrete rib, we can also manually input reinforcement, and we can also run the code-dependent long-term deflection. So with integration member, in terms of design and checks, there are a little bit less options as well. However, they're a little bit easier to work with within the model. That being said, we'll take a look at the results within SCIA Engineer. And first off, we'll take a quick look at the 3D deformation, because you should be able to see that for the first model, obviously we have less stiffness than the second and the third model. So the deformation of that first model, that first floor, should be a lot higher than the second two models. But also, since we gave the same eccentricity for the second and the third model, the deformation should be exactly the same. And that's also what we can see here. The deformation seems to be exactly the same, which is good. And then if you take a look at the 1D internal forces, I can start by looking at the beam and the ribs of this axis. And if I take a look at, for example, the MY of these beams, I can see that for both the first and the second plate, the results are exactly the same. You can also see that within these results, within those moment forces, I have this option rib and integration strip member that I deselected in both cases. Because right now we're actually looking only at the internal forces of the beam part, which is the part beneath the floor. You can also see, if I take into account that third beam, that 1D member, that the internal forces or the internal moment is actually a lot higher. But the difference is that within this model, I'm just looking at the beam and not looking at the internal forces of the plate. And you can also see that the normal forces within that beam are quite high, because obviously these have to be countered by the normal forces from the plate itself. So I already said that SCIA handles this automatically, and I can select this option rib to let SCIA handle this automatically within the ribs. And you can see here that the moment jumps from 13 kilonewton meters to about 70. I can run the same for the integration member. And you can see here that for the integration member, the values are also exactly the same as the model with the ribs. since I'm integrating the forces over the same width within the plate. Now, what is happening exactly when I check these two options? SCIA is looking at the internal forces of the beam, and when I started looking at the results, SCIA was looking at the internal forces of the beam itself and the plate separately. If I check that box for the rib and integration member, SCIA tries to recalculate these values to a rib cross-section where the beam and the plate were together based on a certain width that SCIA either calculates automatically or that I have to set myself manually. And in this case, this was 2 meters. And SCIA will recalculate these forces to get one general cross-section. And how SCIA does this, I've created this little Excel file. Because in the beam we have a certain internal forces. We have a moment force in the beam, a normal force in the beam, and it's the same in the plate. There is a moment and a normal force in the plate. And here we will recalculate these forces depending on the new center of gravity of the cross-section where the beam and the plate work together. And within this Excel file, I created the new center of gravity, and I've calculated this based on the geometric properties of the cross-section. I've calculated the eccentricity of the middle of the plate to that new center of gravity. The same for the beam. I have this eccentricity for the middle of the beam to that new center of gravity. And then I've also added in the internal forces of that beam and rib, which is minus 13.62 kilonewton meters. I've also taken a look at the normal force, which is more or less minus 150 kilonewtons, which is what I have set here. For the plate itself, I've taken a look at the internal forces of the plate, and I've used a section. So I'm taking a look at the result on the sections to know what the internal forces are in that section. And I'm going to start by taking a look at the normal force in that plate. You can see here that above the support, the normal force in the plate is quite high. But if I want to know the average of, or the total normal force over that cross section, I'm going to use the average over that section. And I know that this is twice 1 meter, so I just have to add up these values to get the normal force in the plate. And then I'm doing the same for the moment force My in the plate, because the plate is running in both directions. There's also the plate is also taking up some of the forces. And you can see that the My of the plate is also added in this Excel file. And then basically I'm recalculating this to a normal force in the rib. So I'm just adding up the normal force from the plate and the normal force of the rib. So I get minus 11.15 normal force. I'm taking a look at the moments. I'm adding the moments together, but I'm also recalculating these normal forces to the new center of gravity. And this is giving me a moment in the rib of negative 70.42 kilonewton meters based on all these values. And you can see that if I take a look at the 1D internal forces of that rib, or I'll start by looking at the normal forces. So you can see negative 11.15, which is exactly what I calculated. And the same applies for the moment force My, negative 70.42, which is also what I've calculated in my small Excel file. So you can see here that SCIA is just recalculating the forces from the plate and the forces from the beam to the new center of gravity of that composed cross-section, that composed D-section. If I compare this to the normal forces from the 1D member, you can still see that I'm lacking a little bit of moment. You can see 77 and 70, 44, 37 kilonewton meters. And basically I am missing some part or some forces from the plate since I'm only integrating over a zone of 2 meters. while I'm looking at, if I look at the whole section, you can see that I'm missing some moment which falls outside of that zone, but I'm also missing some normal forces that fall out of that zone. So if I go back to my plate, I'm missing some my and I'm missing some ny from that plate since I'm integrating over a certain width. And that's also what is explained a little bit in the following image, where if you take a look at the left stress profile, this is the real stress profile. This is also what we're getting in SCIA Engineer when you run a 3D calculation, where the stress is not constant over the width of the plate. While if you take a look at the 1D model, and also if you take a look at the integration of the internal forces into a 1D member, is where we get a simplified stress profile where the stress is constant over the effective width of that rib cross section. But if you recalculate these internal forces, we're obviously excluding some of the forces from the plate into that ribbed cross section, so we'll have to take those into account as well. And we can take those into account in three ways. The first option is obviously to take into account the stresses in the plate that are left that fall outside of this effective width. And in that case, we'll have to reinforce the plate a little bit more compared to when you run this as a 1D member. But SCIA also offers some choices or some options how to take into account the forces that fall outside of this plane. So you can see that there are some normal forces that fall outside of this effective width, and SCIA can handle this as well. And the first option to handle this in SCIA is quite simple. And within that first option, we can tell SCIA, okay, I'm gonna make the shape of the rib t-symmetric, or I'm gonna set the shape of that rib myself. Instead of having to have the calculation automatically, I'm gonna set this myself. And in that case, you can change the width for the internal forces and the checks. So I can tell SCIA, okay, I want to take into account the full 5 meters for my internal forces, but for the checks and for the reinforcement, I'm just saying that this is a T-section with a width of 200 millimeters. And with the integration member, I can basically do the same. I can say, okay, this is an integration member with a width of 2.5 meters, while the cross-section that is hanging on that integration member is still that same cross-section with a width of 200 millimeters. So in this case, I'm actually integrating the forces over a larger width. But once I run the reinforcement design, it's going to take a smaller T-section. And in this case, I should get really close to the actual 1D member. Since at this point, I'm integrating over almost the whole width. Although that due to some 3D effects, I'm probably still going to have some normal force in the ribs with the plate compared to the 1D model. But for the moment force, I'm guessing that the results will be very similar to each other. And so let's take a look. If I go back to the 1D internal forces, if I take a look at my rib, my integration member, and my 1D member, I can see that for the moment forces, I'm reaching that 77 kilonewton meters for both the rib with 5 meters of width for the internal forces, as for the integration member, as for the 1D element. So in those additional 3 meters of plate, I've taken up all the forces, so I'm reaching more or less the same values as in the 1D element. But you can also see that probably there are still some normal forces. Yeah, so you can see that there are still some normal forces in these ribs with the higher width. And also, it's quite important to take into account that these internal forces were recalculated to a certain center of gravity. And if I change the width of that rib element, that center of gravity will also change slightly. So that's also a reason why the forces will not match up 100% with this element from the 1D model. but we're more or less at the same values. And then there is one final option, which is only available for the ribs. And for that final option, we're actually going to take a look at the normal forces in the plate. So this only works for the normal forces. There's still moment in the plate as well. That's not being taken into account. But in the final option, you can set within the concrete menu, or you can set it on a member-specific level. You can tell SCIA to not take into account actual force. And I'm doing this for this specific rib element. And if you do so, you can recalculate the actual force to a bending moment. And what that does is basically it is looking at the resulting normal force that is still present in the rib. And in this case, this was minus 11.15 kilonewton meters. And it is saying, okay, this normal force should still be present somewhere in the plate, because the general normal force should equal 0. So it's going to add an additional moment equal to that normal force times the eccentricity of the plate, and it's going to add up that force into the rib. And in this case, this is quite small because the eccentricity is quite small, and also the normal force itself is quite small. And this will also only be available if you go to the concrete 1D internal forces. This is not possible with the regular internal forces. This is only possible within the concrete menu. And if I take a look at this concrete menu, I can see the difference here between the moment force that was calculated earlier, the negative 70.42. And I should also be able to get that MED value, negative 71.19. And you can also see with the normal force that the normal force within the rib has been recalculated and there is no more normal force present. This option is only available for the concrete ribs, and it's only available within the concrete menu. I also had to set this option within the concrete 1D data, but I could have also set this option within the concrete settings themselves. So if we would have gone to internal forces for the ribs, I could have said, okay, for the actual force, I do not want to take actual force into account, and I want to recalculate that actual force to a certain bending moment. And if I do so right now in these general settings, this will be done for all elements. If I do it for a specific element, it's just going to do that for that specific element, and for the other elements, it's going to keep these general settings. You can see by doing so that also the moment force does not equal the moment force that I had from this 1D member. And the reason for that is that in this case, I am taking into account the additional normal force in the plate. So I'm taking into account the normal force that falls outside of this effective width, but I'm not taking into account the moment force in the plate. If I want to take into account also the moment force in the plate, I have to make this rib bigger, give it a bigger width. Or I can also say, okay, in this case, these plates are working in two directions. They are isotropic plates. That's also why I've quickly created this fourth model as well, where these plates are orthotropic plates, where they have an effective height of 5 millimeters in the second direction, which basically means that it has no stiffness in the y direction. So for these plates, there should be almost no moment my that fall outside of this region. You can also see that for these concrete settings, I set the recalculate actual force to bending moments for all elements. So this means that for all ribs, it's going to recalculate this right now. And we can see the difference here where we have a plate that runs in one direction or in two directions. For this second plate, the moment force should also be very, very close to what we have in this 1D model. And we can see that in this case, since I recalculated that initial force, the NED value should be 0 as well. So now that we've taken a look at how SCIA is recalculating and calculating those internal forces and how it is transferring that to a rib cross-section, we can start looking at how SCIA will reinforce these ribs and what the difference in reinforcement will be between those different concepts. And in this case, I've also set some settings in the concrete settings just to simplify things a bit. One of these first elements is that I've not taken into account a lot of detailing reinforcement. So for the plate, I'm not taking into account minimal reinforcement, and I'm not doing that for the ribs as well. And then we'll compare the differences between this 1D segment, between the integration member, where I'm taking into account the forces over a zone of 5 meters, while the cross-section itself is only 2 meters wide. I'm going to compare that to the rib, where the forces are also taken over a width of 5 meters, but the section itself is equal to 2 meters. I'm going to do the same with the rib, where the forces are taking over a meter, but also the same for the checks. And then finally, I'm going to compare that to the model where I have the plate running in one direction compared to the plate running in two directions. And it makes sense that if you have the plate running in one direction, it will not contribute or not have any reinforcement running in that second direction to take up the moment. You should also know that for these elements, these are calculated with these MED and NED values that are the forces that are recalculated. So there are no normal forces in this top beam, for example, NED. There are no normal forces in these ribs, while there are some normal forces in this integration member. And that's also what's going to give some differences. So I'll just start with the concrete 1D reinforcement design. And in this design, SCIA is basically going to try to calculate how much reinforcement you need in the members. And I'm going to do that for that same load case. And I'll start with the 1D member. And if I ask for the required reinforcement for that 1D member, you can see this is a nice baseline where I have about 3.18 square centimeters at the top. And I'll first start off by comparing that to the model where the plate runs in one direction. So I've basically taken into account all of the forces, since I took into account the normal forces within the plate with that option that I set in these internal forces. So right now it is taking into account that actual force by recalculating to a bending moment. And if I take a look at the reinforcement design for that certain rib, you can see that the values match very closely, and in this case they are exactly the same. If I compare that with the concrete rib where I took into account all of the forces as well, but I took them over a zone of 5 meters while it recalculated it, or it's calculating the reinforcement for this section with a width of 2 meters, you can see that it also closely resembles this value, but it's not completely the same. And that is, like I said before, also due to the fact that the center of gravity is slightly different between these two models. And if I compare that with this integration member, you can see that with the integration member, the value at the top is even less than the 1D member, but at the bottom, the value is higher. And that is because if you look at the internal forces of that integration member, there is some normal force that is taken into account. So at the top, there is some compression, which will help for the reinforcement, while in the middle of the span, there is a general tension, which will require more reinforcement. which is also what we're seeing. If you take a look at the results, at the top we need a little bit less reinforcement due to the compression, while at the bottom or in the middle of the span we need more reinforcement due to the additional tension being present there. And then finally we have the last member where I took the rib and where the forces are integrated over the same length as where I make the check, so over that 2 meters of. And you can see here that I need less reinforcement both in the middle span as over the support as the 1D member, because the plate is taking up some of these forces. But this also means that I'll need to reinforce the plate in this model or with this rib more compared to the plates in the other models, because the forces that remain in that plate need to be taken up as well, and we'll need to do that by reinforcing the plate a little bit more. So the difference here is that the member itself, or the Deflection itself, needs a little bit less reinforcement, but the plate needs more reinforcement. While if you look at this from a different perspective and where you take up all of the internal forces in that actual 1D member, the values resemble more or less the same values that you get from the 1D member. This is also quite handy if you take a look at the 2D reinforcement. So if I take a look at a concrete 2D reinforcement design, there's also this option rib that all of a sudden pops up if you take a look at the reinforcement 2D design. And by clicking this option, you're basically telling SCIA that you took into account the forces in the plate for the calculation of the rib. So I'm telling SCIA, okay, for this rib, I took into account the forces that fall in this zone, and you don't need to put in reinforcement in the plate itself. And if you take a look at, for example, at the reinforcement in these 4 plates, let's say the second direction at the bottom, so in the y direction, the direction of the green arrow, we should be able to see that in these zones of the rib there is no reinforcement necessary. You can see the blue zones, there is no bottom reinforcement necessary. And you can see that with the model where we took less forces into account, I need more reinforcement in the plate compared to, or over a larger zone compared to the model where I took these forces into account in the rib itself. So it's a little bit a choice up to the user. Are you taking up all of these forces within the rib, or are you taking up part of the forces in the rib and part of the forces within the plate? If I go back to the concrete 1D reinforcement design, and I'll compare these 2 ribs as well with the integration member, and let's take the 1D member in there as well. SCIA is going to calculate how much reinforcement I need, more or less. But based on a certain template, and you can see here I can edit this provided reinforcement template if I want to. I can also set this template in the beam rib general concrete settings as well. If I change it here, it will be changed for all elements as well. This is basically a template where you tell SCIA, I'm going to place 4 bars with a diameter of 16 at the top, 2 bars of 16 at the bottom. And then when you need more reinforcement, you're allowed to add in bars with a certain diameter and then a certain amount of bars at either the top, the bottom, or on the sides. But by taking a look at the required reinforcement, I can also transfer this to provided reinforcement. And SCIA is going to take a look, okay, I need about this much reinforcement. Then it's going to take a look at that template and it's going to try to find a layout where it can add up the bars to have at least this amount of reinforcement. I can take a look at this provided reinforcement. I can see, okay, this is how much SCIA is going to add. And in this case, this is the minimal reinforcement from the template. But I can also hit the conversion for real bars. And you can see that it uses that same cross section even though I took the whole width for the integration of the internal force, it is taking that same cross-section to input that reinforcement. Can also run the concrete checks on these elements as well right now. So for example, if I want to run the ULS response check on, for example, that integration member and these different, let me run this for a link selection. I can run, for example, the unity check of these three members, and it's going to run that unity check, and you can see that these values are the same as well. If I go back to my overview of the concrete rib versus the regular beam and plate, this is basically what I've done. I've taken a look at the reinforcement auto design. This is possible for the concrete rib and the integration member, but I can also run the concrete code checks for both the concrete rib and the integration member. While at the same time, you can see that this reinforcement manual input and the code-dependent deflection will also only run for the concrete ribs. And if I delete this reinforcement, you can see that I can add in 1D reinforcement in these ribs. And I can add in, for example, user reinforcement in these ribs based on the second template SCIA uses. And in this template, you have a little bit more flexibility as well. I can edit these reinforcements and I can really say how many bars I want at what edge. So this manual user reinforcement is a little bit more flexible. You can really place bars wherever you want. But you can see if I'll add this into the integration member, it's not possible. And if I just select the member, it is recognizing the rectangular cross-section and it is not recognizing that integration member. And you'll also see that if I run this code-dependent deflection, that it's not going to be able to run the code-dependent deflection on an integration member. So I can ask for the, or let's keep that combination. I can ask for the deflection of the required reinforcement for these two members. I want to have, let's say, the required ULS reinforcement for, let's say, cross-section. I'm getting a little warning about the amount of 1D segments, because basically in the code-dependent deflection, SCIA is going to try to recalculate, or it's going to try to calculate the crack stiffness of the element. And based on the stiffness, it's going to recalculate the deflection. But if the element is only one 1D element, or if there's only one section on that element, the stiffness of that whole element is going to be the same. So if it's cracked, the whole stiffness is going to be cracked. While if it's uncracked, the whole stiffness is going to be uncracked. In many cases, however, just the middle will be cracked. So we'll need to split up this beam into different segments. So for example, this part can be cracked, while the rest of it can be uncracked. And this can be done by setting the average number of 1D mesh elements on straight 1D members to a value of at least 5. However, we can already see here that I'm getting a unity check for this rib, but not for the integration member, because the check is not going to run on integration members. And then finally, now that we've taken a quick look at the reinforcement in these ribs and the difference between these integration members and the concrete ribs, where you have a little bit more flexibility with the concrete ribs to get the correct reinforcement, we'll take a final look at the determination of the rib effective width. As I've talked a little bit about before, the real stress profile and the simplified stress profile, where we take constant tension over a certain effective width. And SCIA is calculating that effective width based on the Eurocode formulas. And it's actually going to take a look at the span. And it's going to take a look at either is this going to be the first span, a middle span, or an end span. And if you look at this right-hand side, SCIA is not going to split up the different zones, but SCIA is going to take a look at this span, and this span, and it's going to give the values of these spans equal to whatever the Eurocode is telling, and it's not going to take this into account. In this case, I only have two end spans, so my length L0 should be equal to 0.85 times L1, and I've created a quick Excel file where my length, the width of my element, and so on. And for the first and last zone, the effective width should be equal to 0.2 times my length L0, which is 0.85 L1. But also these other values are calculated, and we can see that indeed the effective width should be equal to 1 meter. While if there would have been a middle zone, which I don't have, the effective width should have been 0.85 meters. And that's also what we can see here. These effective widths have been 1 meter, while I have a separate model here where I created that middle span. You can see that for the middle span, the effective width is indeed 85 centimeters. In this final last model, you can also see, for example, if there have been openings in the plate, I created an opening within this plate. You can also see that SCIA automatically detects this opening, and it adapts the effective width on that side to half the width of my beam. You can see that the effective width is the same as half the width of the beam itself. And then one last thing that is also quite important with this effective width is that SCIA calculates this based on the buckling length. And you can see for these elements here, the buckling settings have been set. And we can see that there are supports. So SCIA recognizes that this is a support, and it recognizes that this is a support. But if I would say that this is not a support, if I'm making this one large span, and if I recalculate this effective width, it is already giving me some error, but you can see that all of a sudden my effective width got a lot larger, and all of a sudden I have 1,470 millimeters on both sides, because right now this is not recognized as a support, so this is a beam that has the full span from the first to the second point. This also means that I need to draw the elements all in the same direction. If for some reason this element was drawn in a different direction, or I can also reverse the orientation of this element. If I recalculate the effective widths, you can see that for all of these elements, or if I take a look at the buckling settings again, this is seen as one element because the first element is running in the first direction. The first element was drawn this way, the second one is running in this direction, and then the third and the fourth one again are running in this direction. So you can see again that I don't have an end span because it's not a continuous beam, it is a single beam. And in that case, it is going to take L0 as the full length, since the effective width is basically the length between the points where the moment is 0. And that will probably be the same as if I would remove these 0.85 values. And I can see here that I'm getting at that 1.12 meter value. So SCIA is calculating the effective width based on the buckling settings, which is something many people forget, but this is also just quite important to know. And this also brings us to the end of our 45-minute webinar session. I want to thank you all for joining me today. And if you have any questions, you can drop them in the comment section, or you're also always welcome to reach out to us through support@scia.net, and we'll get back to you as soon as we can. Thank you.